Hey there, and welcome to Somnifly. Where are we heading off to this time? Let me know in the comments below. Today, we're diving into the fascinating phenomenon of the universe's expansion. We'll explore how space itself is stretching, from the Big Bang to the accelerating growth we observe today. So buckle up, hit that subscribe button, and turn on notifications. You won't want to miss a thing. Let's explore the universe together. Imagine you're standing on a hill at night, looking up at the sky. The stars seem eternal, unmoving, endless. But what if I told you that everything you see, the stars, the galaxies, even the blackness of space itself, is changing, evolving, and stretching apart? That's what modern cosmology is all about, understanding the vast, dynamic, and ever-expanding universe we live in. Cosmology isn't just about pretty pictures from space telescopes. It's the science of where everything came from, how it's changing, and where it's going. And it's a science that has completely transformed over the past century. If you lived a few hundred years ago, you might have believed the universe was eternal, static, and unchanging. Even Albert Einstein, when he first developed his equations for gravity, assumed the universe had to be stable. When his math suggested otherwise, he introduced a fudge factor, the cosmological constant, just to keep the universe still. He later called that his biggest mistake. So, what changed? Observations. A Belgian priest and physicist named Georges Lemaitre looked at Einstein's equations differently. He proposed that the universe might be expanding, stretching outward from a much smaller, hotter, denser state. This idea would later evolve into what we now call the Big Bang theory. Around the same time, a Russian mathematician named Alexander Friedman worked out solutions to Einstein's equations that described a universe that wasn't static but dynamic, either expanding or contracting. The real game changer came when an American astronomer, Edwin Hubble, made a shocking discovery. He measured the distances to galaxies and found that the farther away they were, the faster they were moving away from us. This was the first real observational proof that the universe was expanding. Imagine dots drawn on the surface of a balloon. When you blow up the balloon, every dot moves away from every other dot. That's what our universe is doing. Today, we know that the universe has been expanding for about 13.8 billion years. It started as an incredibly hot and dense state, then stretched out over time, cooling and forming the structures we see today: galaxies, stars, planets, and eventually us. But even now, we're left with some of the biggest mysteries in science. What is the universe made of? How will it evolve in the future? Why is it expanding faster and faster? These are the kinds of questions cosmologists are still trying to answer. And to understand these mysteries, we have to start with the key observation that changed everything: the discovery of the universe's expansion. In the early 20th century, astronomers began to notice something strange about the light coming from distant galaxies. A man named Vesto Slipher was the first to measure the motions of these galaxies by analyzing their light spectra. What he found was unexpected. Most of them seemed to be moving away from us at incredible speeds. But it wasn't until the work of Edwin Hubble in the late 1920s that this discovery turned into something much bigger, something that would change our entire understanding of the universe. Hubble used what's called Cepheid variable stars, special stars that pulsate with a regular rhythm, to measure distances to galaxies. These stars act like cosmic yardsticks because their brightness is directly linked to their pulsation rate. By measuring these stars in different galaxies, Hubble could calculate how far away those galaxies were. And here's where things got really interesting. When he plotted the distances of these galaxies against their velocities, how fast they were moving away from us, he found a clear pattern. The farther away a galaxy was, the faster it was receding. If all galaxies are moving away from each other, then at some point in the past, they must have been much closer together. Rewind the clock far enough and you get to a time when everything in the universe was packed into an incredibly small, hot, and dense state. That's the foundation of the Big Bang theory. Not an explosion in space, but an expansion of space itself. Of course, this raises new questions. If galaxies are moving apart, what exactly is expanding? Is space stretching like a rubber sheet? Does that mean the universe has a center? And what does this expansion tell us about the past and future of the cosmos? To answer these, we need to dive deeper into what it really means for space itself to expand. When we talk about the universe expanding, it's easy to picture galaxies flying away from some central explosion like shrapnel from a bomb, but that's not what's happening at all. The reality is much stranger. Space itself is stretching. Galaxies aren't rushing through some pre-existing space. The space between them is literally growing. Think of it like this. Imagine drawing tiny dots on the surface of a balloon. Now, blow up the balloon. The dots move apart, but they aren't traveling through space. The rubber itself is expanding. That's what's happening to our universe, except it's not just the surface of a balloon, it's three-dimensional space itself. The mathematical framework that describes this expansion comes from Einstein's general theory of relativity and is captured by something called the Friedmann-Robertson-Walker metric. It tells us that space can stretch, contract, or remain static, depending on the overall energy and matter in the universe. When we plug in real astronomical data, we see that space is indeed stretching in all directions at once. Here's where it gets even weirder. If space is expanding, does that mean there's a center to the universe? No. No matter where you are, you'll see everything moving away from you. If you lived in a distant galaxy, you'd see the same pattern, other galaxies moving away in all directions. There's no special point that marks the center of expansion. The universe is like a giant, infinite loaf of raisin bread rising in the oven. Each raisin moves away from every other raisin as the dough expands. But wait. If space itself is expanding, does that mean we're expanding too? Are atoms, people, and planets stretching apart? Thankfully, no. The forces holding atoms together, electromagnetism and the strong nuclear force, are far stronger than the effects of cosmic expansion. Even galaxies and galaxy clusters are bound by their own gravity. Expansion only happens on the largest scales, across vast distances, where gravity isn't strong enough to keep things together. Now, if space is stretching, what does that mean for our ability to see the universe? Are there places so far away that their light will never reach us? Absolutely. That's where cosmic horizons come into play, limits beyond which we can never observe. That's what we'll talk about next. If the universe is expanding, does that mean there's a limit to what we can see? Yes. Even though light travels incredibly fast, almost 6 trillion miles in a year, it still has a finite speed. And since the universe has only been around for about 13.8 billion years, that means there's a limit to how far light could have traveled since the Big Bang. This gives us the particle horizon, the maximum distance from which light has had time to reach us. You might think this means we can only see a sphere around us about 13.8 billion light years in radius. But that's not quite right. Remember, the universe has been expanding while that light was traveling. By the time the light from those earliest regions finally reaches us, the actual distance to those regions is much larger, over 46 billion light years. So our observable universe is actually a sphere about 92 billion light years across. But there's another, even more dramatic horizon, the event horizon. This is the distance beyond which galaxies are moving away from us so fast that their light will never ever reach us, not even if we wait forever. Space is expanding faster than the speed of light at those distances, carrying galaxies beyond our reach. That means there are parts of the universe that, in principle, we can never observe or interact with. They exist, but they might as well be in a completely separate reality. Now, you might wonder, if the universe is finite in age, why isn't the sky just filled with endless starlight? Wouldn't every direction eventually lead to a star? This was a classic paradox known as Olber's paradox. If the universe were infinite, static, and eternal, then the sky should be blindingly bright, because every line of sight would eventually hit a star. The reason it's dark? The universe is finite in age. There simply hasn't been enough time for distant light to fill the entire sky. So we live inside an observable bubble, surrounded by ancient light from galaxies that are, in reality, much farther away than they appear. And that light, it's stretched, redshifted, by the very expansion of space itself. That's what we'll dive into next. If the universe is expanding, what happens to the light traveling through it? Well, something fascinating. It stretches. This phenomenon is called cosmological redshift, and it's one of the most important clues we have about the expanding cosmos. Imagine you're holding a slinky and slowly pulling it apart. The coils stretch, just like the wavelength of light does when space expands. The farther away a galaxy is, the more its light has been stretched on its journey to us. Instead of appearing in its original color, the light shifts toward the red end of the spectrum. The more distant the galaxy, the more extreme this redshift, meaning we can use redshift as a cosmic speedometer to measure how fast galaxies are receding. Now, this is not the same as the Doppler effect, the one you hear when an ambulance siren changes pitch as it moves past you. The Doppler effect happens when something moves through space, but cosmological redshift happens because space itself is expanding, carrying galaxies with it. It's a fundamental difference. These galaxies aren't moving away in the usual sense. They're being pulled apart by the fabric of space itself. And redshift doesn't just affect color, it changes time itself. Imagine watching a supernova explode in a distant galaxy. If that galaxy has a redshift of 1, the light waves have doubled in length. But that also means that everything happening in that galaxy, supernova explosions, star formation, even time itself, appears to be happening twice as slowly from our perspective. The greater the redshift, the more extreme this time dilation. If we look back far enough to the earliest galaxies, we're not just seeing them as they once were, we're seeing them in slow motion. So why does this matter? Because redshift is one of the most powerful tools we have to test our models of the universe. The way light stretches, the way time slows down, it all perfectly matches the predictions of an expanding cosmos. And when we map out these redshifts, they tell us something even deeper, the geometry of the universe itself. If we could step outside the universe and look at its shape, what would we see? Is space curved? Is it flat? Does it wrap around in some strange way? These are the kinds of questions that take us into the realm of cosmic geometry and topology. First, let's talk about geometry. According to Einstein's general theory of relativity, the shape of the universe is determined by its total mass and energy. Space itself can be curved by gravity. The more mass there is, the more space bends. And just like in everyday geometry, there are 3 possibilities for the overall shape of the universe. If the universe has too much mass, space is curved positively, like the surface of a sphere. If you travel far enough in one direction, you could eventually return to your starting point. This would be a closed universe, finite in size, but without any edges. If the universe has just the right balance of mass and energy, space is flat, like a giant infinite plane. Parallel lines stay parallel forever, and the rules of Euclidean geometry hold perfectly. This is what we call a flat universe. If there's too little mass, space is curved negatively, like a saddle. Parallel lines would eventually diverge, and the universe would be open, stretching infinitely in all directions. So which one is it? Well, thanks to precise measurements of the cosmic microwave background radiation, the leftover light from the Big Bang, we now know that the universe is very, very close to being flat. The tiny temperature fluctuations in this ancient light act like a cosmic ruler, and when we compare them to theoretical models, they tell us that our universe's curvature is either exactly 0 or so close to 0 that we can't measure the difference. But geometry isn't the only question. There's also topology. Even if space is flat, that doesn't necessarily mean it's infinite. Just like a video game world that wraps around when you reach the edge, the universe could have a strange looping shape where traveling in one direction could eventually bring you back to where you started. This is an open question in cosmology. We still don't know for sure whether space extends forever or whether it has some hidden structure beyond what we can observe. So, we have a universe that's geometrically flat, but possibly topologically weird. But what is it actually made of? That's the next mystery. Let's talk about the cosmic recipe, the ingredients of the universe. If you took everything we see, stars, planets, gas clouds, even all the people on Earth, it would add up to almost nothing. All the visible matter in the universe makes up less than 5% of what's actually out there. The rest, it's something far more mysterious, dark matter and dark energy. Let's start with the normal stuff, the baryonic matter that makes up you, me, and everything we directly interact with. Protons, neutrons, Electrons. This familiar matter is what forms galaxies, stars, and planets. But when astronomers started looking at galaxies in detail, they noticed something strange. In the 1970s, astronomer Vera Rubin studied how galaxies rotate. According to Newtonian physics, stars on the outskirts of a galaxy should move slower than those near the center, just like planets in our solar system. But when she measured the rotation speeds of galaxies, she found that stars in the outer regions were moving just as fast as those near the middle. This made no sense unless there was some unseen mass providing extra gravity. That invisible mass? Dark matter. We now know that dark matter makes up about 25% of the universe, and it acts like a cosmic glue, holding galaxies and galaxy clusters together. We can't see it directly, but we know it's there because of its gravitational effects. We see how it bends light around galaxy clusters in a process called gravitational lensing. We see its imprint in the cosmic microwave background radiation. And yet, we still don't know what it actually is. It's not made of ordinary atoms. It doesn't emit, absorb, or reflect light. The leading theories suggest it could be some kind of exotic particle that barely interacts with normal matter, except through gravity. But as mysterious as dark matter is, it's not the biggest puzzle. That title belongs to dark energy, a force that makes up a staggering 70% of the universe and is literally pushing space apart. In the late 1990s, two independent teams of astronomers were measuring the distances to distant supernovae, exploding stars used as cosmic mile markers. What they expected to find was that the universe's expansion was slowing down over time due to gravity. But instead, they found something shocking. The universe's expansion is actually speeding up. Something is counteracting gravity, stretching space apart faster and faster. That something is what we call dark energy, and we have almost no idea what it is. One possibility is that it's related to Einstein's cosmological constant, an energy embedded in the very fabric of space itself. Another idea is that our understanding of gravity needs modification at cosmic scales. Either way, dark energy is the dominant force shaping the future of the universe. So here's the big picture. The universe is mostly made of things we don't understand. 5% normal matter, 25% dark matter, 70% dark energy. And yet, these unseen forces completely determine how the cosmos evolves. Now, if dark matter is real, it should be doing something important. It should be shaping galaxies, clustering them together, and influencing cosmic structures on the largest scales. And that's exactly what we're going to explore next. If dark matter is invisible, how do we know it's really there? Because without it, the universe as we see it wouldn't exist. Galaxies wouldn't have formed, stars wouldn't have clustered together, and we wouldn't be here to talk about it. Think about the early universe. Right after the Big Bang, everything was a hot, dense soup of particles. There were tiny fluctuations, slight differences in density. Some regions had just a little more matter than others. Over time, these denser areas attracted more and more material due to gravity, eventually growing into galaxies and galaxy clusters. But here's the problem. If we only count the normal matter, the protons and neutrons we know, there simply isn't enough gravity to explain how these structures formed so quickly. This is where dark matter comes in. It doesn't interact with light, but it has gravity. And that means it was the first thing to start clumping together in the early universe, forming invisible scaffolding, gravitational wells, that normal matter later fell into. Without dark matter providing that extra gravitational pull, galaxies wouldn't have had enough time to form before the universe expanded too much. We can see dark matter's effects in multiple ways. One of the most striking is gravitational lensing, when the gravity of unseen dark matter bends and distorts light from distant galaxies like a cosmic magnifying glass. We can also study it by looking at galaxy motion. Without dark matter's extra gravity, galaxies and clusters would fly apart instead of staying together. One of the best pieces of evidence comes from a galaxy cluster called the Bullet Cluster. It's actually two galaxy clusters that collided. The normal matter, hot gas, slammed together and slowed down, but the dark matter passed right through without interacting. When astronomers mapped where the mass actually was, they found that the majority of the gravity came from regions where there was no visible matter at all. That's dark matter in action. Now, the big question, what is dark matter? We still don't know. The leading theory suggests it's made of some unknown particles, maybe WIMPs, weakly interacting massive particles, or axions, which interact through gravity but barely with anything else. There are experiments underground, in space, and at particle accelerators trying to detect it directly. But while we're still figuring out dark matter's true nature, its role in shaping the universe is clear. And as mysterious as it is, dark matter isn't the only thing driving cosmic evolution. Because as we saw earlier, something even stranger is at work. Dark energy. And it's changing the fate of the universe itself. For most of cosmic history, gravity was in charge. It pulled matter together, forming galaxies, stars, and clusters. But in the past few billion years, something else has taken over. Something that's not just counteracting gravity, but pushing space apart faster and faster. That mysterious force is dark energy, and it's reshaping the destiny of the universe. The first big clue came in the 1990s when two independent teams of astronomers were measuring distances to distant supernovae, exploding stars used as cosmic mile markers. They expected to find that the universe's expansion was slowing down over time due to gravity. Instead, they found something completely unexpected. The expansion was speeding up. The farther away a supernova was, the more its light was redshifted, meaning space had stretched more than expected. This was shocking. For decades, astronomers had assumed that the universe's fate depended on how much matter it contained. If there was enough mass, gravity would eventually slow expansion down, maybe even reverse it, leading to a big crunch. If there wasn't enough, expansion would continue forever, but gradually slowing down. Nobody expected acceleration. The simplest explanation for this repulsive force is something called the cosmological constant, an idea that actually goes back to Einstein. When he first developed his equations of general relativity, they suggested that space should be expanding or contracting. Since no one at the time thought the universe was expanding, Einstein added a term to his equations to keep the cosmos static. He later called it his biggest blunder, after Hubble's discovery of expansion. But now it turns out that something very much like Einstein's cosmological constant is real. This constant represents an energy embedded in the very fabric of space itself, vacuum energy. Unlike normal energy, which dilutes as space expands, dark energy stays constant or even grows. The more space expands, the more dark energy there is, leading to even faster expansion, a runaway effect. But what is dark energy, really? That's one of the biggest open questions in physics. Some theories suggest it's related to quantum fluctuations in empty space, a property predicted by quantum mechanics. Others propose it's a new unknown force, something even stranger than Einstein's equations. And some physicists think our understanding of gravity itself might need revision at cosmic scales. Whatever dark energy is, we know one thing for sure: it dominates the universe. Today, it makes up about 70% of all energy in the cosmos, and it will determine the universe's ultimate fate. Will expansion continue forever? Will galaxies drift so far apart that the night sky goes dark, or could dark energy change over time, leading to an even more dramatic ending? To answer that, we need to step back and look at the full history of the universe, how it evolved from a hot, dense beginning to the vast cosmos we see today. The universe wasn't always cold, dark, and expanding. In its earliest moments, it was a seething, energetic fireball, a place where matter and energy were almost indistinguishable. Over the past 13.88 billion years, it has gone through dramatic transformations, from an opaque plasma to a cosmos filled with galaxies and stars. Let's take a journey through cosmic history. At the very beginning, the universe was incredibly hot and dense, so hot that atoms couldn't even form. Instead of normal matter, everything was a soup of fundamental particles, constantly colliding and transforming into energy and back again. But as the universe expanded, it cooled down, allowing different forms of matter to emerge at different times. In the first fraction of a second, the universe was dominated by radiation, light and high-energy particles bouncing off each other. This was the radiation-dominated era, where energy was so intense that normal matter couldn't clump together. But within minutes, things changed. As temperatures dropped, protons and neutrons combined to form the first atomic nuclei, mostly hydrogen and helium with tiny traces of lithium. This process, called primordial nucleosynthesis, set the stage for everything that would come later. For the next 380,000 years, the universe remained a glowing plasma where light couldn't travel freely. But then something amazing happened: recombination. Electrons finally paired up with nuclei, forming neutral atoms. Suddenly, space became transparent, and the first light from the early universe was released, the cosmic microwave background radiation, which we can still detect today as a faint glow across the sky. But the universe was still dark. No stars, no galaxies, just expanding gas. That changed when gravity slowly pulled matter into the first dense pockets, sparking the formation of the first stars a few 100 million years after the Big Bang. These stars were huge, hot, and short-lived, producing the first heavy elements: carbon, oxygen, and iron, through nuclear fusion. When they exploded as supernovae, they seeded the cosmos with the ingredients for planets, life, and everything we see today. As stars grouped into galaxies, a new cosmic structure emerged, the era of galaxy formation. Over billions of years, galaxies collided, merged, and evolved into the massive structures we see now. At the same time, the balance of cosmic forces shifted. In the early universe, matter dominated, shaping the cosmos through gravity. But a few billion years ago, dark energy took over, accelerating the expansion of space. Today, we live in an era of accelerated expansion, where galaxies are drifting apart faster and faster. The structures we see now, galaxies, clusters, superclusters, are locked in place by gravity. But as time goes on, expansion will stretch space so much that distant galaxies will eventually disappear from view. So what's next? If we look even farther back, beyond this smooth expansion, we find something even more radical. The moment the universe exploded into existence. That's the story of cosmic inflation, and it might hold the key to understanding why our universe looks the way it does. Let's dive into that next. The Big Bang might have marked the beginning of the universe as we know it, but what if I told you that something even more dramatic happened before that? A moment of exponential expansion, faster than anything we see today, a phase called cosmic inflation. Imagine the universe as a tiny speck, far smaller than an atom. Now imagine that, in a fraction of a second, that speck expanded by a factor of at least 10 to the 26th power. That's a 1 with 26 zeros after it. This isn't just expansion. This is expansion on a scale so extreme that a subatomic region stretched to the size of the observable universe almost instantly. But why do we think inflation happened? Because it solves some of the biggest mysteries in cosmology. First, there's the horizon problem. When we look at the cosmic microwave background, the leftover light from the Big Bang, we see that it's amazingly uniform in all directions. But in a normal expanding universe, regions far apart should never have had time to exchange information because nothing can travel faster than light. So how did they end up at the same temperature? Inflation solves this by saying that the universe started as a tiny connected region, Schlein, where temperature could equalize before it expanded beyond causal contact. Then there's the flatness problem. As we discussed earlier, the universe appears to be geometrically flat, but under normal expansion, any tiny initial curvature should have grown dramatically over time. The fact that it didn't suggests that the universe was stretched into flatness, exactly what inflation would do, just like how the surface of a balloon appears flatter as it expands. And then there's the absence of magnetic monopoles, exotic particles predicted by some theories that we should see if the early universe was hot enough. Inflation dilutes them away, explaining why we don't find them. But what caused inflation? The leading idea is that a mysterious quantum field, called the inflaton field, drove this rapid expansion. Just as normal fields, like an electric field, have energy, the inflaton field had a special kind of energy that repelled gravity, pushing space outward at an exponential rate. Eventually, inflation ended, and the energy of the inflaton field transformed into matter and radiation, kickstarting the hot Big Bang. And here's where things get truly mind-blowing. If inflation happened once, could it happen again and again in different regions of space? Some models suggest that inflation never completely stops, that instead our universe is just one bubble in an ever-growing multiverse, where other bubbles with different physical laws might be forming all the time. But before we get too speculative, let's ground ourselves in something we know happened: the formation of the first atomic nuclei. Right after inflation ended and the universe cooled, the first elements, hydrogen, helium, and a bit of lithium, were born. And that's what we'll explore next. As the universe emerged from the fury of inflation and settled into a hot, dense state, a new process took center stage: nucleosynthesis, the birth of the first atomic nuclei. This was a brief but crucial moment, setting the chemical foundation for everything that would come later: stars, planets, and even life itself. Let's rewind to about 1 second after the Big Bang. By this time, the universe had cooled to a few billion degrees, still far hotter than the core of the sun. It was a dense plasma of protons, neutrons, electrons, and photons, all colliding in a chaotic dance. But as the universe continued to expand and cool, something remarkable happened. At around 100 seconds, conditions became just right for nuclear fusion to begin. Protons and neutrons started sticking together, forming the first elements. The main products: 75% hydrogen, 25% helium, and tiny traces of lithium. These are the primordial elements. Everything else, from carbon to gold to uranium, would have to wait for the first stars to forge them billions of years later. Why didn't heavier elements form right away? Because the universe was cooling too fast. In stars, nuclear fusion happens over millions or billions of years, carefully building up elements like oxygen and iron. But in the early universe, there was only a brief window, about 3 minutes, where conditions allowed fusion to happen. After that, the temperature dropped too low for nuclei to collide with enough energy to fuse further. That's why the early universe ended up with mostly hydrogen and helium, the simplest and lightest elements. But the story doesn't end there. Neutrinos, tiny, nearly massless particles, also played a role. These ghostly particles were created in huge numbers during the first few seconds and then streamed freely through space. Even today, a vast sea of cosmic neutrinos still fills the universe, though they're almost impossible to detect. And then came a major turning point: recombination, about 380,000 years later. Electrons finally cooled enough to combine with atomic nuclei, forming the first neutral atoms. This was the moment when the universe became transparent, allowing light to travel freely for the first time. That ancient light, the cosmic microwave background, is still visible today, carrying an imprint of those first atoms. So what started as a chaotic, searing hot plasma had now cooled into a calm, neutral gas, drifting through space. The universe had entered its dark ages, with no stars, no galaxies, just vast clouds of primordial hydrogen and helium waiting for gravity to take over and build the first cosmic structures. And from there, everything began to take shape. The first stars ignited, galaxies formed, black holes grew. The universe as we know it was born from these simple ingredients, shaped by cosmic forces beyond our imagination. But our journey doesn't end here. The universe has a way of leaving behind fossilized evidence of its past. And one of the most extraordinary examples of this is the cosmic microwave background radiation, or CMB, a faint glow that fills all of space, a direct remnant from the time when the universe was just 380,000 years old. Let's take a step back. In the first moments after the Big Bang, the universe was a hot, dense plasma of protons, electrons, and photons, all constantly colliding, scattering, and interacting. This meant that light couldn't travel freely. The cosmos was essentially a glowing fog, opaque to radiation. But as the universe expanded, it cooled. When the temperature dropped to about 3,000 degrees Kelvin, something dramatic happened: recombination. Electrons slowed down enough to combine with protons, forming neutral hydrogen atoms. Suddenly, light, once trapped in the chaotic plasma, was free to travel. That first burst of escaping radiation is what we now see as the cosmic microwave background. Now, here's the fascinating part. Because the universe has been expanding for billions of years, those original high-energy photons have been stretched by the expansion of space itself. What started as searingly hot radiation in the visible and infrared range has now shifted into the microwave portion of the spectrum, with an average temperature of just 2.7 degrees above absolute zero. The discovery of this radiation was one of the greatest moments in modern cosmology. It was first predicted by theorists in the 1940s, but nobody actually detected it until 1965, when two radio astronomers, Arno Penzias and Robert Wilson, were testing a new antenna. They kept picking up a mysterious background noise. No matter where they pointed their instrument, the signal remained. At first, they thought it was some kind of interference, maybe even pigeon droppings on their equipment. But soon they realized they had stumbled upon the afterglow of the Big Bang itself. This discovery confirmed the hot Big Bang model and ruled out competing theories like the steady-state universe. It showed that the early universe was indeed once a hot, dense state that cooled over time. Since then, scientists have launched space telescopes like COBE, WMAP, and Planck, which have mapped the CMB in exquisite detail, revealing tiny temperature fluctuations, the seeds of galaxies and clusters that formed billions of years later. But here's something mind-blowing. There are more CMB photons in the universe than any other type of particle, billions for every proton and neutron. And even though today they make up only a tiny fraction of the universe's energy, they once dominated cosmic expansion, shaping the early evolution of everything we see. So this faint microwave glow isn't just a random background hum. It's a snapshot of the infant universe, frozen in time, carrying messages from an era long before the first stars were born. And by studying it, we can unlock secrets about dark matter, dark energy, and even what happened before the Big Bang itself. Now, how do we actually measure this radiation? What patterns does it contain? And what strange anomalies have we found that hint at new physics? That's where we're headed next. If you think of the cosmic microwave background as the faint afterglow of the Big Bang, then studying it in detail is like reading the universe's birth certificate. The temperature, patterns, and tiny fluctuations in this radiation hold an astonishing amount of information about how the cosmos evolved and what it's made of. On average, the CMB has a temperature of 2.7 degrees above absolute zero, incredibly cold but uniform across the entire sky. The key word here is almost. If the early universe had been perfectly smooth, galaxies and stars wouldn't exist today. But tiny variations, about 1 part in 100,000, are scattered across the CMB, revealing the earliest imprints of cosmic structure. These temperature variations, or anisotropies, come from small density fluctuations in the early universe, regions that were slightly hotter or colder than their surroundings. Over time, gravity amplified these variations, pulling matter into dense regions to form galaxies, clusters, and filaments of cosmic structure. By studying the patterns of these fluctuations, we can extract key cosmological parameters. Things like the total amount of matter, the proportions of dark matter and dark energy, and even the shape of the universe itself. But measuring these tiny temperature differences isn't easy. Earth's atmosphere absorbs much of the microwave radiation. So to get a clear view, astronomers have launched space-based observatories. The first major breakthrough came with the COBE satellite in the 1990s, confirming that the CMB followed an almost perfect black-body spectrum, exactly what the Big Bang model predicted. Then came WMAP, which mapped the temperature fluctuations in far greater detail. And most recently, the Planck satellite provided the most precise measurements yet, showing that the universe is remarkably flat, confirming predictions from inflationary cosmology. So, how does the CMB tell us about cosmic geometry? The key is something called the sound horizon. In the early universe, matter and radiation were tightly linked, forming waves of compression and rarefaction, essentially sound waves rippling through plasma. When the universe became transparent, these waves left behind distinct patterns in the CMB. The largest of these patterns, about one degree across on the sky, corresponds to the maximum distance a sound wave could travel before the universe be transparent. If the universe had positive curvature, like a sphere, we would see these fluctuations as appearing larger than expected. If it had negative curvature, like a saddle, they would appear smaller. But what we actually see is a perfect match with a flat universe, one where parallel lines never meet, and the rules of Euclidean geometry hold. Beyond geometry, the CMB also captures later cosmic events. About 400 million years after the Big Bang, the first stars and galaxies formed, emitting powerful ultraviolet radiation that reionized the intergalactic medium. This left a subtle imprint on the CMB, affecting how we see those primordial fluctuations today. And there's more. As CMB photons travel across the universe, they pass through galaxy clusters filled with hot gas. When these photons interact with electrons in the gas, their energy shifts slightly, an effect known as the Sunyaev-Zeldovich effect. By studying how the CMB is distorted, we can actually map the distribution of galaxy clusters billions of light years away. In short, the CMB is more than just the oldest light in the universe. It's a cosmic blueprint, a data-rich fingerprint of everything that has ever happened in the cosmos. And as our technology improves, who knows what hidden secrets we might still uncover. But one question remains. What about the anomalies? Could certain oddities in the CMB hint at new physics or even something beyond the observable universe? That's what we'll explore next. One of the most remarkable things about the cosmic microwave background is that it changes over time. It's not just a fixed temperature frozen in space. It evolves as the universe expands. And this gives us a unique way to test our cosmological models. According to the Big Bang Theory, as the universe expands, the temperature of the CMB should decrease in a very specific way. It should be directly proportional to the scale factor of the universe. In other words, if we look back in time, when the universe was half its current size, the CMB should have been twice as hot. When it was a tenth of its current size, the CMB should have been 10 times hotter. The amazing part? We can actually test this. How? By looking at how the CMB interacts with matter at different points in cosmic history. One way to do this is through excited atomic and molecular states. Certain atoms and molecules, like carbon monoxide, molecular hydrogen, and cyanogen, can absorb or emit radiation at very specific wavelengths. When we look at distant gas clouds, we sometimes find these molecules in an unexpectedly excited state, as if they're being illuminated by a faint glow. That glow? It's the relic radiation from the young universe. This effect was actually first observed in the 1940s, long before the CMB was officially discovered. Scientists noticed that molecules in interstellar space seemed to be excited, as if they were being warmed by a background radiation of about 3 Kelvin. But at the time, no one realized they were seeing the signature of the Big Bang itself. Today, we can use this method to measure the CMB temperature at different redshifts, tracing how it has changed over billions of years. And the results match predictions perfectly. As we look further back in time, the CMB gets hotter exactly as expected. The second method relies on something called the Sunyaev-Zeldovich effect, a kind of energy exchange between CMB photons and the hot plasma inside galaxy clusters. Here's how it works. The CMB photons travel freely through space, but when they pass through massive galaxy clusters, they collide with high-energy electrons in the hot gas. These collisions give the photons a little energy boost, shifting them to slightly higher frequencies. As a result, when we look at a galaxy cluster, we see a tiny dip in the lower energy CMB photons and a slight excess of higher energy ones. The key detail, the amount of energy gained depends on the initial temperature of the CMB. So by analyzing how the CMB changes as it passes through different galaxy clusters, we can directly measure its temperature at different points in time. And once again, the data shows that the temperature of the relic radiation scales exactly as predicted by the expanding universe model. This is yet another independent confirmation of modern cosmology. It tells us that not only is the universe expanding, but it has always been expanding in exactly the way our models predict. But this also raises a bigger question. Could anything have disrupted this smooth cooling of the universe? Are there hidden effects that might hint at new physics beyond our current theories? That's what we'll explore next. If you could rewind the universe to its earliest moments, you wouldn't see galaxies, stars, or even atoms. Instead, the cosmos would be filled with tiny density fluctuations, quantum-scale ripples in space that eventually grew into the vast structures we see today. Galaxies, clusters, and cosmic filaments stretching across billions of light years. These initial variations in density weren't random. They followed a specific statistical pattern, which we can still observe today in the cosmic microwave background. The temperature fluctuations we see in the CMB, just 1 part in 100,000, are the faint imprints of those ancient density differences. Over time, gravity amplified these tiny irregularities, causing denser regions to pull in more matter and form the first cosmic structures. But here's the key question. Where did these fluctuations come from in the first place? Modern cosmology points to inflation, the period of ultra-rapid expansion that took place in the first tiny fraction of a second after the Big Bang. During this phase, quantum fluctuations in the inflaton field, the energy field driving inflation, were stretched to macroscopic scales. These quantum ripples became the seeds of all structure in the universe. We can test this idea by studying the power spectrum of the CMB, the way temperature variations are distributed across different angular scales in the sky. The largest features correspond to regions where density fluctuations had just enough time to grow before the universe became transparent. Smaller features reflect acoustic oscillations in the hot plasma of the early universe, waves that move through the primordial soup of baryons and photons. One of the most important patterns in the CMB is the Doppler peak, which occurs on scales of about 1 degree on the sky. This corresponds to the sound horizon at the time of recombination, the maximum distance that sound waves could have traveled before the universe became transparent. These waves were driven by the interaction between normal matter and photons, and their imprints tell us a great deal about the composition and geometry of the universe. The CMB's acoustic peaks, the smaller features in the power spectrum, contain even more information. Their amplitudes depend on how much baryonic matter was present in the early universe, while their positions reveal whether space is curved or flat. Observations from WMAP and Planck confirm that our universe is remarkably flat, matching the predictions of inflationary theory. But there's more. Inflation predicts that these primordial fluctuations should be Gaussian, completely random, with no preferred scale. And that's exactly what we see in the CMB. The patterns of density variations are precisely what we would expect from quantum fluctuations stretched by inflation. And it doesn't stop there. Inflation also predicts the existence of tensor fluctuations, primordial gravitational waves that should leave a distinct pattern in the polarization of the CMB. Detecting these patterns would provide direct evidence of inflation, and scientists are currently searching for them using ultra-sensitive telescopes. So when we map the cosmic microwave background, we're not just looking at ancient light, we're seeing the fingerprints of quantum fluctuations from the dawn of time, frozen into the structure of the cosmos itself. And before we wrap up, here's a fun fact. Right now, my channel is like a tiny star with only 2 subscribers shining in the vast cosmos, just 998 more, and will light up a whole new galaxy where YouTube starts paying out. If you want to fuel this journey to interstellar fame, check out the links below. Thanks for watching, and see you in 4K.